Good afternoon. My name is Garner and I live in New Zealand in a small town called Pleasant Point in South Canterbury. I designed the Garner GR-2 as my entry to the Royal Aeronautical Society's 2019 design competition. I would like to start this brief overview of the design with a video of the aircraft flying in the simulator. As you can see from the specifications here, the aircraft is very small, only 10 feet from the tip of the pitot on the nose to the tip of the spinner on the aft end. The small size provides for low weight, low drag, and with the 150 kilowatt electric motor driving it, top speed is predicted to exceed 300 knots indicated. From studying the rules, it was apparent to me that the two primary constraints were the fixed maximum power and the minimum wing area requirement. The other rules I considered less significant from a performance standpoint. I chose three primary goals for the design of the aircraft: minimize size and weight, minimize wetted area, and maximize laminar flow. All of these, of course, with the goal of minimizing drag. Here we have a comparison of the GR-2 next to a Cassette 1, an aircraft designed for the same racing purpose, albeit with a conventional power plant. The drawings are to scale, though it appears at first that the GR-2 is unreasonably small, as the Cassette is already a very small aircraft. However, if the Cassette was tailless as well, the comparison appears somewhat more reasonable. The GR-2 design is a tailless flying wing. The motor is mounted behind the pilot, driving a pusher propeller, and this may be an advantage in the real world, as the prop could ingest and accelerate the boundary layer around the aft fuselage, where the pressure gradient becomes adverse. The undercarriage is of a tricycle type with a small retractable nose wheel, and the main gear is mounted to the wing at the point where the extended strake section transitions to the primary tapered wing segment. The main gear fairings extend upward and aft into a large wing fence, the trailing edges of which are small rudders. These wing fences provide sufficient yaw stability and reduce spanwise flow on the inboard section of the moderately swept wing. Pitch and roll control is provided by ailerons on the outer wing. Split flaps are incorporated under the short section of wing between the fuselage and the wing fences. These provide increased drag to permit normal approach angles and increased lift to allow reasonable landing speeds without an angle of attack high enough to risk a prop strike. The pilot has an excellent view as the nose slopes down, providing an unobstructed view forward, and the wings sweep aft, providing superior vision to the sides and below. The small protuberances you may have noticed at the wing root and after the canopy are ram air inlets for cooling the batteries and electric motor and systems. The slight drag penalty for this style of inlet was considered worthwhile to ensure a high pressure and consistent flow of cooling air at all times. Overheating batteries or other systems are more likely to lose a race than marginally slower lap times. Here we have a proposed internal layout. The main wing spar extends from tip to tip, passing behind the pilot's seat. The batteries are mounted inside the wing strake section, ahead of the main spar, and immediately outboard of the fuselage. This location of the batteries allows for a significantly smaller fuselage, while distributing the mass of the aircraft further along the wing, reducing the bending loads at the wing root. The motor is mounted behind the main wing spar. There is adequate room around the motor for installation of necessary systems, such as the motor controller and other ancillary devices. Depending on the actual mass of the batteries installed, the motor location may be moved fore or aft by inversely varying the length of the motor mount and the prop shaft extension, thus maintaining a correct centre of gravity even with changes in the battery technology. Approximate control runs are shown connecting the pilot controls to the ailerons and the flaps. you may notice there is no mechanical connection to the rudders. To save weight and simplify the role of the pilot, the rudders are computer controlled via electric actuators to maintain a 0 beta angle automatically. It is proposed that a small knob or a lever mounted to the throttle or stick would permit the pilot to command left or right yaw from the computer as required. The system is intended as an optimization, keeping the aircraft pointed directly into the relative airflow for minimum drag. Manual control of yaw is no more difficult than for any other aircraft type, despite the novel configuration. The setup also eliminates the rudder pedals and the control linkages, reducing weight, and allows for a smaller, tighter forward fuselage as the pilot does not need to move their legs to depress the rudder pedals. The main undercarriage mounts to the front of the main spar, immediately outboard of the batteries in the wing. The small nose gear retracts into the space under the pilot's knees. Should the nose gear fail to extend for landing, only minor damage will be expected to the fuselage under the nose. This has been demonstrated many times on routine canard types and is easily repaired. The key feature of any aircraft is the design of the wing. This is especially true of a tailless design to obtain good stability and control on the pitch axis. For the GR-2, new airfoils were designed to perfectly suit the aircraft. The airfoils change considerably along the span and are designed to promote extensive laminar flow to minimize drag. To provide stability, the camber of the airfoils reduces further outboard, becoming slightly negative at the tip. Little geometric twist is required. Polars of one of the wing airfoils are shown here at Reynolds numbers bracketing the aircraft's flight envelope. Actual airfoil shapes are similar to what you can see in the renderings, with the point of maximum thickness well aft. While the wing design is very efficient for the intended purpose, going fast, it has limited lifting capability, so the stall speed is relatively high for the wing loading. The stall itself is mild and is quickly recovered. Positive control is maintained throughout, and effort is required to induce the aircraft to drop a wing. In this video clip, the aircraft is being flown at minimum speed with throttle at idle and the controls fully aft. The aircraft handles in a conventional manner with no unusual characteristics besides the yaw control. Stability is very good in all axes, allowing the pilot to readily position the aircraft very precisely on the race course. In turns at full race speeds, the wing is operating very close to its maximum lift-to-drag ratio. As a result, very little energy is lost in turns. Due to the unexpectedly high speeds possible with this design, G-forces in the turns can also exceed those that the airframe is required to be able to sustain according to the rules. The highly reclined position of the pilot will provide good protection from the effects of the high G-forces. The design of the aircraft lends itself well to high loads. All heavy parts are located close to the main wing spar, so the fuselage structure does not need to be particularly heavy. The mass of the batteries is carried inside the wings themselves, as previously mentioned. The design of the wing itself tends to minimize bending loads. Most of the lift is produced inboard and very little near the tips. When pulling into a turn, the elevons deflect upwards, unloading the outer wing and thus further concentrating lift inboard. That's my design entry into this year's competition. Despite the unusual design, or rather because of it, it is fast around the course, much faster than I anticipated. I have attempted to be conservative with the figures input into this design to ensure that the output is reasonable and possible to achieve in reality, and maybe someday soon we'll find out. Thank you for the opportunity to present my design to you this afternoon. A special thanks to those in the Royal Aeronautical Society who made this competition happen and patiently answered questions that I asked along the way. If anyone would like to contact me for any reason, you can reach me via my website, xaerodynamics.com. I hope I'll have the opportunity to meet many of you at a future RAeS event. You may find me cleaning bugs off the leading edges of a small flying wing. Thank you.